Hi, welcome to this video series about staying relevant in the age of knowledge automation, which I like to call From the Mess to the Man. These videos are about the science behind the technologies that affect our daily lives. And these days, this often translates to questions like, will AI take my job? So we're going to talk about some of these technologies and what they are, what they're not, what they can do, what they can't. But more importantly, I'm going to talk about the most valuable traits of human intelligence, like critical thinking, the kind that is irreplaceable now and will continue to be for the foreseeable future, and how using these traits together with science and tech literacy will help you navigate today's world. This doesn't mean that everyone needs to become a scientist or an engineer to survive some sort of AI apocalypse, but we are in the 21st century with 21st century tech, so the kind of basic common knowledge that everyone needs to know needs to be updated for our times. It will also probably help increase anyone's chances against being fired and replaced by an AI agent, an AI browser, an iPhone Air, whatever tech companies come up next with. In this first video, we're going to talk about the rise of the machines, meaning how come is AI suddenly everywhere and how it became so good that even jobs like programmer or data scientist that were considered safe just a while ago and actually helped build some of these models, or build them actually, are threatened by this technology. We're also going to answer questions about what's inside these kind of chatbots, like is it magic or something? But yeah, I'm just kidding. Like there's no magic, to be clear, or alien technology or conscious involved in how LLMs work. But we will, though, get into some version, like some serious version of some of these questions later. By the end of this video, we're going to have like a good general idea of what were the recent advances and conditions that make these new applications possible. What are the current limitations of the technology that can be overcome in the short run, and otherwise what are like limitations that will continue and being part of them and persist in many other ways because they are intrinsic to how these things work and will not go away anytime soon. Let me introduce myself very briefly. I'm Caetano Sotomayor. I'm a scientist with background in math and statistics applied to the natural sciences. I have, among others, I have a master's degree in quantum chemistry, a PhD degree in computational biology, and further research experience in several other subfields. But you can check my webpage or this academic aggregator web pages for academic indices, or my LinkedIn profile to verify my credentials. And credentials and qualifications are important, but they do not speak for themselves. I speak for myself. And the most important thing that I actually need to transmit about my background is that I'm a scientist who's been using statistical models in my research for well over a decade, like actually more like 15 years at this point. I also teach math and statistics in universities and other institutions. But more importantly, I spent like a decade and a half arguing with bench scientists on how to use these math and statistical methods of different sorts. And now that everyone is trying to use these models, whatever they can, to be able to put AI in the titles of their papers, I feel vindicated on the one hand, but I also increasingly feeling the need to separate the wheat from the chaff and fight against the tide of just trying to use the computers indiscriminately. And yeah, so it don't become a society that is over reliant on technology and that doesn't like trust machines blindly. Anyway, without even more ado, let's jump right into the first episode then. Well, not right in, quite a bit before. But anyway, this is not a lecture on the history of computers and algorithms. That will go back like several centuries and be like very complex and long. But I think it is important to have like a general context for our current like AI powered quote unquote world. And modern computer algorithms have been around for the better part of a century, and the internet has been around for over a couple of decades, a little bit over a couple of decades. But it feels like just a few years ago, with the release of ChatGPT, is that the term AI is like absolutely everywhere. and people are wondering like, wow, was this new technology, and is this it? Is this when machines take over a large part of like society and everyday activities, creates like ruptures or conflicts? Do we have to fight for our own survival? Are we going to be enslaved for bioelectrical energy like the Matrix, um, or some Terminator like scenarios? And because it's like all seemed for most people so sudden, um, it made it seem that AI just sprung up overnight, but it was actually conceived quite a while ago. As I mentioned, computers existed before that, and initially they were specialized and not as powerful, and they became more widespread. And all of a sudden, well, again, not all of a sudden, but at some point in time, it seemed like they were just everywhere, and they were just used for every kind of task. Um, and maybe what's happening with AI is that it's following this exponential growth in computers, and we're seeing a similar pattern, which we're gonna try to explain a little bit about as well. Um, if we go way back, even that before the concept of AI even existed, before computers existed, and even when modern science maybe was like quite young, so that we couldn't talk about like sci-fi genre, maybe like more like fantastic novels. Um, Even at that time, like art already imagined things that could resemble AI somehow. So I want to quote like the whole thing literally here, and it says the following: Everyone knew how laborious the usual method is of attaining to arts and sciences, whereas by his contrivance the most ignorant person, at a reasonable charge, and with a little bodily labour, might write books in philosophy, poetry, politics, laws, mathematics, and theology, without the least assistance from genius or study. And that's from Jonathan Swift's Gulliver's Travels, and that's from 1726. And it does an incredibly accurate job of describing what ChatGPT would be able to do in 2022. So it predicts almost to the year, like 300 years before, like 3 whole centuries before what we are kind of seeing now in a lot of ways. Um, but more concretely, like beyond fantasy and sci-fi, it was at least as early as 1950 when Alan Turing had already the thought about whether machines could think. And he phrased that in a more careful way, talking about like if the behavior of a machine could be indistinguishable from that of a human for another human who's interacting with them. And that's the origin of the Turing test. Today we know that it's not a very accurate measure of intelligence either. Um, but that, at least at the time, they were already thinking about that with a more realistic basis, which was Turing's machine, the Turing machine itself. But it was finally in 1955 that the term artificial intelligence was coined, and that was in a kind of summary research proposal from John McCarthy from Dartmouth, Marvin Minsky from Harvard, Nathaniel Rochester from IBM, and none other than Claude Shannon from Bell Labs. And it wasn't necessarily like a name that everyone agreed with, the term artificial intelligence. It's pretty obvious that it stuck and it's the most used at this point. Um, but also it wasn't just the name that was a source of disagreement. It was also the approach that was going to be used. On the one hand, there was the kind of symbolic AI, also known as rule-based, and almost synonym with good old-fashioned AI. These are all pretty much synonyms, which means that computers would be programmed to respond to instructions with a series of rules, and they would be given the rules of how to react. And once you coded everything into the computers, they would be able to react to any situation. And the other approach will be sort of statistical AI, which is also pretty much synonym, not exactly the same necessarily, as machine learning, which is the basis of the kind of large language models that we see today, which is like diametrically opposed in philosophy to the symbolic AI. There are no rules that are hard-coded into machines. Instead, there are models that are given data, and the responses of the machine need to be similar to what is in the data, and the model is supposed to process that. So if you're talking about language, you have data on language, and the machine would learn. The term machine learning comes from that kind of thing. How to respond once it's presented with a sentence, and interacting with a human, which is the ultimate goal in that sense. So just from these two examples, which don't have to be like the only examples for how to reproduce artificial intelligence, we can see that there's no single or obvious way of how to reproduce intelligence. What we can say is that the statistical approach was more successful, at least measured by adoption today. And so that's what we see right now. But we don't know if that's going to lead to some more accurate reproduction of actual human intelligence, if something that can be scaled and improved indefinitely. We just know that that's what we're seeing right now. Research and development wasn't always steady either. There were at least a couple of what are called AI winters in the development of these machine learning and AI models. And today, computers are just like almost like another appliance, a little bit cooler than like a fridge or a toaster. But at the time, it was completely revolutionary. They could automate things to that level and create so many different things with a machine that would be able to process things as fast as it could in a very general way. So it seemed like completely limitless. So why not try to program like something that is intelligent? If it can process really fast, it could like think really fast and access amount of data and knowledge that no human could, and create something super intelligent, which is what people are talking about today. But yeah, it's not just because like it's cool and in theory it could be possible, or it's like a interesting idea, that in practice it would actually be possible. And that led to after years, decades of development, that the results weren't as amazing, as awesome as many people or most people that were there like expected. And there started to be some pushback. One of the most notable moments was a paper by James Lighthill, which became known as the Lighthill Report, which was used to justify or not the further investment in AI research in the UK. And there was an assessment of the different applications and the results that were found to be like at best kind of disappointing, and at worst like complete failures of the promises that were made of the technology. So there was, because of that report, well, not because, but kind of coinciding and correlated with some of those efforts, there was the first AI winter, which lasted until the late 70s. Back in the 80s, there was some activity that picked back up AI research, but again, there was some cooling down towards the end of the 80s and 90s through the beginning of this century. It's also considered an AI winter. And the lesson that people say that was learned from that was not over-promising, making realistic goals, setting realistic goals, and trying to not overhype a product if it was not going to for sure deliver something. It's not clear to me at all that's something that they did learn, but that's what is said, that it was learned from those AI winters until research starting to pick up again. And why did research start to pick up again? Well, what changed in the 21st century is that basically computing power continued to increase, kind of doubling every 1.5 years. That's Moore's law for CPUs, which are central processing units. And I'm not one to endorse like the more is more model for everything, but it is true that towards the end of the 90s, and I've seen like that change personally. Yeah, I'm probably that old that I like had a small IBM in the 80s that I used to use, and then how it changed to the beginning of the century as an adult, how much it changed in terms of applications by the time I went to university and started doing research. One example is Markov chain Monte Carlo, which is an inference algorithm that relies on a lot of simulations and sampling and processing sequentially, which was basically impossible to do for a long time. It was a great idea, but it just didn't work in practice, and that started to be used, and that was something that cracked a lot of problems once it was practical to do. Just to be clear with the abbreviations, as I mentioned, CPU or central processing units, and it was basically the entire computer in the 80s or 90s. That was basically what did all operations that a computer needed to do. But by the end of the century, they were kind of hitting a limit in how fast they could be made, mostly because of the size of transistors that would fit into a single chip. So one thing that companies started to do was to divide processors into multiple cores that could do parallel processing. And and also for completeness, GPUs, they're different from CPUs. They're graphical processing units, and they're different because they were designed to make many small calculations. They're not as precise or powerful as CPUs, but they're used for the kind of calculations like graphics, hence the name that they have, like graphics in video games, and that's when they were first developed by Sony, for instance. I also grew up to see that. Like, you had some cartoon games like Mario on the Nintendo and Super Nintendo, and PlayStation and Nintendo 64 was like completely different ball game with the kind of graphics because of the development of these GPUs. And as it happened, this kind of architecture from the GPUs was exactly what was needed for the kind of machine learning models that we're now seeing, like neural networks, which are the basis of deep learning methods, which are also the basis of large language models. And that's basically what made NVIDIA the most valuable company in the world. It's a story about getting rich selling shovels during a gold rush, right? So training LLMs requires a lot of energy and computing power, and a lot of small, simple operations are done in these kind of neural networks. It's kind of a brute force approach to computing the billions or trillions of weights that are the parameters in these neural networks, and more on that later, what are the weights. But GPUs were designed to do exactly this kind of calculation. You may hear another different kinds of processing units, although CPU and GPU are the most prevalent, especially GPUs. It's what is talked about all the time. Google has TPUs. It developed TPUs, which the T stands for tensors, because that's like the kind of format of the data. They're not necessarily tensors formally, but they have the shape of tensors, which are arrays of numbers that are not only a single row like a vector or list, or not even a matrix, two-dimensional. They can have any number of dimensions, and it speeds up some kind of computations. If you have processors that are optimized for that kind of structure, maybe you can do things faster than with a regular GPU. That's very niche, and it's only for Google, and most people they rely on general GPUs because only Google makes these TPUs apparently. You may also hear about NPUs, which are neural processing units, and they have this name to make reference to neural networks, but they don't have anything neural or necessarily optimized for neural networks necessarily. They're basically kind of GPU-like co-processors that normally go into main CPU, like these newer Intel Core Ultra or AMD Ryzen, that have these processors for the kind of machine learning application. They're optimized for that. They're also cheaper and more energy efficient, so that you can have it in mobile devices and laptops. But ultimately, no one's going to use those for the real, like the heavy lifting of neural networks. They're more like mobile and laptop kind of thing. So in that sense, AI development kind of mirrors like general digital technology, software, and algorithm development. And with the great power comes like more possibilities and more irresponsibility, because they'll build like bigger things just because they can. And then we'll go from there and see what happens after these things are built. It's also worth noting that some of the limitations of the neural network-based approaches that exist. There are like dozens or hundreds of kinds of machine learning models, and every now and then someone might find like a clever way of getting around some of the more computationally intensive numerical calculations of some of these models and enable something that before was impossible, because they mathematically bypassed a lot of computations that needed to be done. But for deep learning algorithms, the approach has been since many years now to basically put more data and make bigger models, which means more calculations, more compute, more GPU power, but also more pollution. So it's kind of an environmental nightmare that these things have to be scaled up indefinitely to be able to achieve something. But we're also starting to see the limits on that we're not going to be able to, or companies rather, won't be able to just scale their way to much more general and better technology. Here I'm going to maybe get a little bit ranty, hopefully not too much. But as I mentioned before, machine learning is a kind of statistical AI, which means statistical models. It's basically what it means, and that's what I have always worked with. There wasn't a term for that, but I like to differentiate between statistical modeling and machine learning. I don't want to get into the beef of like statistics versus machine learning and call machine learning glorified statistics or rebranded statistics or poorly done statistics, which a lot of people do. That's not the point here. I think there are differences in the practice of statistical modeling versus machine learning. But it's also true that there's an element in marketing in, say, machine learning, because it sounds more advanced somehow, or maybe it used to. And so there's an element of marketing in changing the terminology to make it like more palatable for larger audiences or funders or like Silicon Valley people or something like that. It's more interesting certainly to say that a computer or a machine is learning or that it's being trained than to say we're doing parameter estimation. But I'd also be like remiss to say that there's like nothing new in machine learning that doesn't exist in statistical modeling. It's the same math. There's like little to argue about that, and everything could like just move forward and be done with the name statistical modeling and all the terminologies that existed before without having to come up with new names. The term machine learning is not like new marketing stuff either, though. It was created just a few years after artificial intelligence was coined. So the goal was to make machines learn. But through statistical AI, which is statistical models, it was basically using this approach, but it basically does the same thing. All that was done, but the computer power was not enough for that to happen. So yeah, again, I'm not a historian of technology, and reality is like, of course, like more complex than just like simple cause and consequence, or like one or two causes and some consequence. But I do see two separate things happening in parallel that were very important for like the rise of AI as we see it today. And one was that internet companies were accumulating a ton of data, and two, there was increased compute enabled by large scale were enabled in large scale that enabled these data-driven algorithms to be developed and deployed because of this availability in compute. And because of these two phenomena that didn't always happen like in parallel or to be done not necessarily made for one another, we see some terminology changes, just like statistical models became machine learning. With data, we had data mining at some point, up to the like 2010 or so. people still refer to the user large data sets as data mining, and that's a fitting name because it means you have like a mountain of hard data, and you go there with like a pickaxe to try to pick something that is valuable, and you have to kind of know what it is to be able to find it. And after that, other terms became more popular, like big data. And big data is maybe not very descriptive, but it actually is quite descriptive. It just means that the data is big, but it doesn't say much else about anything, and that's kind of how it worked. There's nothing in big data that says how you need to do it. It just means lots of data. And again, you needed to have a way of systematically extracting data from this big data, this big pile of data. And that's a time when people were also afraid of like algorithms, because Google had the best search algorithms, a lot of user data. Facebook had a lot of personal data, and many other companies were acquiring or obtaining data and using it basically to serve ads and things like that. So people were worried because they would exploit this data, and they did. They exploited this data to serve ads, to sell services, so on and so forth. But it was still reliant on having an algorithm and having a specific targets and making simple associations between that. So big data was not much more than data mining. It was just again kind of a marketing shift to try to sell something different. And finally, I think the value of the amount of data only became completely clear with the arrival of large language models and the right large language models, for that matter, the ones that could generate realistic data. Because and I think large language models is a much better terminology than AI, because it gives a more accurate description of the thing that they actually do. But I guess at the time when that became popular, AI was already too embedded in society for it to be replaced with large language models. Because sometimes AI can be a large language model, sometimes it can be, people will call even a logistic regression AI sometimes. So yeah, it was too late at that point, and AI, Gen AI, so generative AI, in short, Gen AI, agentic AI, which doesn't mean a lot either, reasoning AI, which doesn't really reason, and whatever other derivative buzzwords came up were already kind of all over the place, and sadly they're quite inaccurate or overly generic to describe what is actually done, and so it's not very informative. But here they are, and that's how things evolved in terms of terminology, from statistical AI and statistical modeling to machine learning and AI and LLMs and so on. So yeah, we have to be mindful of how these terms are used, because they don't always mean what people want you to think they mean. But yeah, I want to also make a slightly technical, but not too much, interlude about this kind of AI resurgence, AI spring, or whatever it's called. And yeah, I don't really want to do this, but it's and it's not really a technical thing, but I might have come across it as an AI skeptic, and that's not necessarily the case. So I do want to acknowledge the advances and the improvements that made these tools practical, and that they have value in many areas of life and research. Maybe not as people say, probably not as what most people say, and companies especially want to sell. So with a disclaimer that I'm not an AI skeptic or pessimist, but I am trained in science and statistics. So I do have, and I have a generally low tolerance for hype and bullshit. So I don't play well with promises, or over promising, overselling, as I mentioned, which was kind of the doom of AI in the 70s and 80s, and maybe it was creating a bubble now. But anyway, this was supposed to be when I say good things about AI. But yeah, anyway, so back to the good things about AI. Yeah, transformers architecture, which is what is used in GPT, with it like a generative pre-trained transformers. That's what GPT stands for, if I remember well. Didn't make notes on that. Wasn't in the original script, but anyway. So the transformers architecture of neural networks, which is also like a bad name because everyone thinks of Transformers, like the toy thing, movie, whatever. And the associated components to that, like self-attention, attention, word embedding. These really allowed languages to be treated like vectors in a context space. So it was really efficient, it wasn't efficient compared to what was before, at least. Bridge between language and math, natural human language and math. So this was perfect and made a world of difference, because now there was a perfect way for the mathematical tools that existed in neural networks and machine learning in statistical modeling to be able to manipulate words, because there were now vectors, and there are a lot of, there's centuries of knowledge on how to manipulate vectors. So this created an interface between human language and math, and then as a consequence between language, math, and images, video, code, basically everything that you could possibly embed as a vector now was open to being treated through these like machine learning models. So seemingly overnight, again, not overnight, but it seemed like that was the case, you could write something in plain language and a neural network would convert into a synthetic output that you could plug into all sorts of applications, be it text, video, code, so on. All of that is from not only computer power, GPUs, and amount of data. It wasn't just like more is more. It was also a few clever changes and developments in how things were presented that allowed all of that to like funnel data in and have outputs that are what we are seeing today. To get back to statistical inference for a little bit, I'm not going to get too technical or technical at all, because it's not a point of these series to get technical on this. What they say in science is that when you start writing an equation, you lose half of the audience. I'm not doing that here. Even for scientists, it can be off-putting. But yeah, what is happening is that like some language that used to be obscure statistical jargon is now in the mainstream media. Like training is now a term commonly used to describe how companies get their models to work. And people also say that models are learning, that machines are learning. Machine learning is like already gives away that basically they were supposed to be learning. And we see headlines like OpenAI bought a gazillion GPUs from NVIDIA for the latest model training, or Anthropic's model learned to do college level math. And training, I think it became more popular recently in this frenzy of AI models. And it's machine learning specific terminology that means exactly the same as inference, statistical inference or parameter estimation in old school statistics. In plain terms, it means that a model, and LLM is a model, it's nothing more than a model, has parameters, and we don't know what their values are. We can just like plug in values to the LLM and have it do its thing. What we need is data and some algorithm that allows us to inform this model about what parameters would best match the ones that could produce what we're seeing in the data. So once we have these values, we can leave like the data set aside, and the model can go on to generate synthetic data. That is what can be used in the real world. And in the context of LLMs, that means that engineers estimate the parameters of these huge models, and once they estimate these parameters, the users, they use a product that has these parameters in them, and when you type, they generate data that resembles the original data set that was used to train, quote unquote, these models. So while LLMs are huge models with lots of like quirks and details that can generate text in a very, very convincing way, the statistical foundations are the same of fitting a line to a bunch of data points. It's been done literally for centuries in statistics, there's nothing new in the process itself, and what it's the basic concept of having data, having a model, and having a method that you can then generate data from. So understanding like inference conceptually, you don't have to learn formally what that is, but understanding what is being done is essential to understand how large language models work, and what they can do, and what AI can and cannot do in general. Anyway, you probably figured out at this point that I like to talk about math and science, and if you made it up to here, thank you. But let's like wrap up with kind of some take-home messages that I made some notes for. So one of the most important things that you can take home from this is that AI is a generic term. It's like a general, at this point, overly generic term that borders on meaninglessness at this point, because everyone wants to say that they're using AI to surf the AI wave. So it's not a very useful thing to say we're using AI at all. Machine learning, and especially LLMs, require like a ton of data, as I mentioned, and computing power. And that's one of the reasons that it took like decades for us to get here. And all of that is inserted in a paradigm where you need a lot of data, and you have to increase the use of computers to enable what we have now and to improve, but we're starting to see the limits of that. So LLMs and machine learning models, which are statistical models, so there's no magic involved. There are complicated models, but they're based on like well-known principles of statistics and statistical modeling. So they're limited by these same principles. They're not a whole new thing that is unknown. We don't know how all of these models think and do what they do necessarily, but we know exactly the math that goes into that, and we know the principles of statistical modeling. So we can confidently say many things about models, not unlike what some people try to say. This is the end of our first video series. No, video, not video series. Just video. You're not ending the series here. As promised, if you didn't have a concrete idea of what artificial intelligence was, now you know how and when it was defined, and you also have a general idea of how these technologies advanced and became possible, and their strengths, their limitations. In the process, I also mentioned some concepts like parameters, inference, fit, synthetic data, and so on. I didn't go deeper into their definitions or get technical about it, and that was on purpose because that would be a very different video. If you'd like to learn more in depth about those, you can check out our other courses at auroracollective.io. In our first course, From the Math to the Masses, we teach how to apply critical and scientific thinking in the context of large language models, machine learning, and statistical modeling in general. And in our second course, Putting the Intelligence into the Artificial, we teach the mathematical and statistical foundations of these methods hands-on, and we do it for professionals at every level of proficiency in math and coding. There's no set level to get started with that. So check it out at auroracollective.io. That's Aurora as in Aurora Boreal. I like Aurora Boreal sounds, but anyway, Aurora Boreal. Collective as in not individual, and IO as in input output. It's the obvious geek extension for this stuff, other than AI, but yeah, that'll be too on the nose. In the next video, we're going to talk about more serious failures of artificial intelligence, risks, and some other thorny questions about LLMs and their trustworthiness. So stay tuned for that. If you found this video useful or you enjoyed, please like and subscribe so you stay up to date with the next videos coming out in the channel and in this series. That's a very YouTuber thing to say. Again, I'm not a YouTuber, so I'm not used to this at all, but maybe I'll get used to it. So anyway, yeah, stay relevant and see you next time.